Hi, this is Mr. Doro. Today we're going to be talking about titration of acids and bases. By the end of this, I'm hoping that you can describe the process of titration and make calculations related to titration. Titration involves an acid-base neutralization reaction, which we remember is an acid reacting with a base. They neutralize each other, break each other down to produce a salt and water. The salt is just a general term for any ionic compound. And so we can do our own little acid-base reaction. And if I just picked the weak acid, acetic acid, HC2H3O2, reacting with the strong base, NaOH, then what that is going to produce is a salt. The salt is going to come from the acetate ion and the sodium ion, and I'm going to check the charges on those. Those happen to both be a plus 1 and a minus 1, so that is NaC2H3O2, sodium acetate, which would make a good supersaturated solution, and the thing that's left over is the H and the OH, which is water, and so we would just put H2O. That is an example of a neutralization reaction. These two students right down here are doing a neutralization reaction, adding an acid to a base to make it neutralized here. But they're doing this qualitatively because they're not really measuring things out, not quantitatively. We want to make sure that we do things quantitatively when we're doing a titration. So titration is different because it is a quantitative process. It's a controlled addition of a measurement of a solution with known concentration to a certain amount of solution with an unknown concentration. If you look at this picture that we have here, this is a setup for titration. This is a glass tube right here, kind of like almost like a big straw with a little stopcock on the bottom that you release it, and this is graduated so that you can measure the volume. You put a standardized solution in there. Standardized solution means that you know the concentration of whatever it is. It could be an acid or a base that you put in there. And then you figure out the volume that you have to deliver in order to neutralize this. In this flask, you have the opposite. If this was an acid that you have in here, you have a base in here. If this is a base, you have an acid in here. That is the one that you don't know the concentration of, but you do know the volume of it. So you know the volume of this, you know the concentration of this one, and you keep adding this until you get it neutralized, and we'll talk about how you know when it's neutralized, and you'll end up figuring out the volume of this. So this is the setup for titration. So how do you know when it's neutralized? Well, we're going to talk about the signs that you're going to see when it's neutralized, but this is the reason why it is neutralized. It's when you get the moles of acid equal to the moles of base. When those are equal to each other, then it's neutralized. Now there's a formula that goes along with this. This is kind of just like the dilution one, where we said the moles before you diluted it to the moles are equal to the moles after you diluted it. And so there's a formula for this that we're going to write out, and that formula is MA, that's molarity of the acid, that's the concentration of the acid, times VA, that's the volume of the acid, that's what the A stands for, equals MB times VB. And if you remember, molarity times volume, when you do that, you're going to get moles, because this is moles per liter, and this would be in liters, or it could be in milliliters, because they would cancel each other out. But they would cancel the volumes out, and you're just left with moles of acid equal the moles of base. When they're equal to each other, it is neutralized. When we have the moles of the acid equaling the moles of the base, that's something we call the equivalence point. This is a graph of a titration of a strong acid being titrated with a strong base. We have the strong acid inside the flask here, and we're adding some strong base to it. As we add the strong base to it, the pH starts to go up a little bit, starts a very low pH, and then there's a big jump right here at 50 milliliters that you see, and then it starts to go up a little bit more at a time after that. This is called the equivalence point. At this point right here, when we added 50 milliliters of the strong base, then the moles of acid were equal to the moles of base, and we get this big jump. This happened to be at a pH of 7 because it's a strong acid. It's being titrated with a strong base. When you do a weak acid with a strong base, the pH is going to be higher. Even though there is still an equivalence point, the pH ends up being higher. And if you were doing a weak base with a strong acid, the pH would end up being lower. But we're looking for that equivalence point where the moles of acid equal the moles of base. So the way we determine the equivalence point is we use an indicator. An indicator is either a weak acid or a weak base that changes color at a certain pH that we add to the whole titration process. And so we have to pick the indicator that we're going to use based on what type of acid, if we have a weak acid or a strong acid, and a weak base or a strong base. And so you can see there's a bunch of different indicators that are listed here. Each one of these is a different indicator, and it shows you the color change at different pHs. The one that we're going to use for strong acid and strong base is phenolphthalein, and you need to know that a phenolphthalein endpoint happens between 7 and 9. We'll talk about what endpoints are here in just a second. But you need to know phenolphthalein, and that's the most important one for us in our class. You also could use a pH meter. This is a pH probe that actually measures the pH. You just put it right in there, and it'll give you a more precise measurement of the pH. So you pick your indicator based on where the color change happens, what pH you know that the color change is going to happen, and so you pick an indicator to use for your titration. As we saw on the last slide, depending on the indicator that we use, they will have a different color change at different pHs. The color change is called the endpoint. This is phenolphthalein right here. These are 3 examples of phenolphthalein titrated to different levels. Phenolphthalein is in an acidic solution, is clear and colorless. In a basic solution, it's this pink or reddish color. So when we're titrating and we're adding base to this over and over and over again, as we add base, it'll start to turn pink and it'll disappear, and we've swirled it around. We want to get to the point, the equivalence point is when we get this light pink color. If we get to this pink color right here, or reddish color, then we added too much, and we either have to add acid back to it or restart it, start the whole process. So this would be called a phenolphthalein endpoint, which tells us that we have changed from our acidic solution and we've reached the neutralization point and we're done with our titration. So to do a titration calculation, you got to first of all start out by writing the balanced equation. The reason you have to do that is because you have to know if the strong acid or strong base that you're using to titrate is going to produce only one proton or hydroxide ion, or if it's going to produce 2 when it breaks down. And that would be if it's diprotic or not. And then you determine the molarity of the standard, and that's easy to do based on your balanced equation. Then you just use this formula, MAVA equals MBVB, to determine the unknown. So you're going to know 3 out of the 4. If you use a strong acid to titrate, you're going to know the molarity of the acid, and you'll know the volume of the acid that you had to deliver to get to the end point. You'll know the volume of the base that you started out with, and you have to calculate the molarity of the base. And if you titrated with a strong base, you'll just know these things over here, and you'll be calculating the molarity of the acid. Here's a titration problem that involves a strong base being titrated into a strong acid. So you start out with 20 milliliters of the strong acid, in this case it's nitric acid, and you knew the base, what the concentration of the base was. It is a standardized base with 0.0119 molar, and you needed 31.4 milliliters of it to neutralize it to reach the equivalence point. So what you have to do is you have to start out by writing the balanced equation, which I did right here, checking the charges. I made sure I checked the charges and crisscrossed on this one. When I balance the equation, I end up needing a 2 right here and a 2 right there. And notice that you also had to know what nitric acid's formula was, because it didn't give the formula in this. Now, the reason this is important to write the balanced equation is because you see that this strong base right here produces 2 hydroxide ions for every BaOH2. That means when you have this molarity of BaOH2, you're going to get twice the molarity of hydroxide ions, and that's what is the important part in this. So now we use our formula MAVA equals MBVB. Our VA is our volume of our nitric acid, right up here, 20 milliliters. Our MB is 0.0119 molar, but remember, each one of these produce 2 ions of hydroxide. So what I have to do is I have to multiply this one by 2. 2 times that, and then my VB is my volume of my base, which was 31.4 milliliters. So I just solved for MA. And the answer I ended up getting was 0.0374 molar, or 3.74 times 10 to the minus second molar, and that is going to be HNO3, because that is nitric acid. And that would be your answer. Now you only have to do this multiplication when you have two ions that are being produced on there. If you didn't have that, then you wouldn't do this. If it didn't make the two ions, if this was just something like LiOH, you wouldn't multiply by 2. So here's a problem that I'd like you to do. It's giving you, saying you had 20 milliliters of a 0.1 molar hydrochloric acid, and so you need that to neutralize 30 milliliters of sodium hydroxide. Write out the balanced equation, and then use MAVA equals MBVB and determine the molarity of the sodium hydroxide. And the answer has been provided for you right here so that you can check it out, see if you did it right. Have a good day.